Very good. So hello everyone. Now we start the session two with Dr. Garrett on micrometeoroids and space debris. So go ahead, Dr. Garrett.
Okay, meteoroids and space debris. That's going to be the topic we're covering this afternoon. Let me see, I get it. Oops. Oh, I see what's wrong. Anyway, this was given to me by the leading expert in micrometeoroids, Bill Cook at NASA Marshall, and I always thought this was a pretty good introduction. This is what people really think of when they think of meteors. Anyway.
Can you read some of the captions there? It's difficult here.
Oh, you want to read them? Well, the one in the lower left as well. I guess the little chicken was right. He smashed with a meteorite. Then the other one up in the right, Foxtrot, it says, these meteor showers are always such a letdown. And good morning to you too. And then the other one doesn't have a caption. It just shows everybody bashed up from the meteorites. You'll see in a moment why we did this. Anyway, Chepelinck had a big super bolide hit, and thousands of people were hurt and damaged. It was like the Tunguska fall, only it was over a populated area. This is over Chicago, and this just to show you that it can happen in your backyard too. And this is the guy that got hit.
Oh, yeah.
That's what he got hit with. But that thing must be worth a fortune. Anyone where they hit somebody, you can really sell them. Anyway, this is the scary chart. This is from my friend Pete Warden, close colleague. But this is what the one of our satellites records every day. And this is from 1998 to 2002. These are kiloton events observed around the Earth or larger. I want you to take a close look at that. That's what's falling on us every day.
In 4 years, yeah.
Yep. Now, look at on the right, if you look at the lower right, to the right of moon, you'll see a little dot. What Bill Cook has been doing is he set up a bunch of 14-inch, I think they were Meade telescopes all around the world, so they can look at the dark part of the moon, dark side of the moon, the shadowed part of the moon at any given time, and record the meteor impacts. And you know why? The problem is this: the meteor in and of itself may not hit an astronaut, but they kick up a heck of a lot of debris, and the debris comes back down and can kill the astronauts. And so you can see in the lower picture there what's going on. One little meteoroid can cause a huge avalanche of garbage, and so it's a real issue for us going back to the moon. That's why they want to go down in caverns, because they're afraid they're going to get hit with meteoroids. Now, this is a satellite. This was at, I believe, at AFRL in Albuquerque. This is the satellite before, excuse me, good cough. Anyway, that's before, that's after. A 1 gram particle going about 6 kilometers per second hit that. Most things are going a lot faster than 6 kilometers per second. 6 kilometers to 7 kilometers, about all we can actually accomplish on here, except if you go to the nuclear fusion facilities. Turns out that most guns, where they actually shoot pellets at things, can only go up to about 10 kilometers per second. And you can kind of, if you can figure out how to do it, shoot 2 of them at each other and get up to maybe 20, but they don't really do that. The problem is that by the time you get up to 10 kilometers per second, these barrels are about 20 feet long or something. They have to rifle them. The rifling melts after 1 or 2 shots, and so it's extremely expensive to fire things up at around 6 kilometers per second. Now, there is another thing. You know, the nuclear fusion facility, like in Livermore and stuff, where they use lasers to focus on a particle, pellet, and use that to do fusion. Well, it turns out sometimes the laser beam isn't balanced, and it'll kick the pellet out at up to 30 or 40 kilometers per second. So when we were getting ready to go, JPL was getting ready to go by the sun, we lost out to Goddard. I mean, not Goddard, but oh heck, forgetting the name of Applied Physics Lab, APL. When we lost out, but we were getting ready to go to one of those nuclear facilities and have them deliberately bounce a particle off us at those velocities, because that's the velocities you'll see around the sun. But anyway, 10 kilometers per second, totally disintegrated, 1 gram. Think about how small 1 gram is. These are some of the satellites that have been destroyed.
Yeah, what was the scale of that?
I'm sorry, what?
What was the scale of that satellite model?
Probably about a half a meter to a meter.
So, okay.
You can see the back door there, where they brought it in. So it was a big garage door thing.
Right.
It looks like it's a leftover, what was it? Transit satellite.
Yeah, it probably was. Yeah. Anyway, it's done in Albuquerque as best I remember.
Well, that was Project Polar Bear was one of them where they picked one up out of the Smithsonian and launched it, but I didn't heard about this one.
Yeah, I was involved in it indirectly. Anyway, the bottom line is that's what it looked like afterwards, supposedly. Anyway, these again are from Bill Cook. A lot of this stuff is from Bill Cook because he gives the main presentation for NASA on meteoroids, and we'll see some of the other people who give the other talks. We all trade presentations. Anyway, this is one of my colleagues did this for me. This is all the missions that have been damaged by micrometeoroids that we know of, and you can see it's quite a few. Mariner 4, for example, the satellite went by Mars and slowly died. And what they traced it back to was one of the batteries they believe was holed by a micrometeorite. It went through a stream, and they think that it got holed at that time and then slowly leaked out, and the satellite died afterwards. But there are lots of these things, and when they fly through the rings of Saturn, they get all kinds of little micrometeoroid impacts that they can detect from the RF, and with Cassini, for example, or with Voyager. And then the solar probe has these real long antenna arms on it, and they pick up the little impacts from the micrometeoroids, the micron, tens of micron size particles. They're constantly causing RF noise. And the big one was IC3. They had really long antennas on that. And as I understand from the French, the antenna is small in diameter, and therefore a small micrometeoroid can break it. And it broke the antenna, but the two antennas were balanced. And when that went, the whole satellite spun out of control because they cut the balancing antenna. Anyway, this is my meteorite collection. I was going to show you where they go. We start with the iron nickel. That's the iron one up there, the Chicote alien. Then you go to what are called pallasites. The pallasites are the most valuable ones, other than the Mars ones, because they're beautiful. And you can see this is a light shines in behind it, and it's like stained glass. It's this one's from Russia. They've got a whole bunch of them from where the nuclear accident took place, Chernobyl. This is called a Chernobyl pallasite, and I did test it. It's not radioactive, but it was right next to the reactor. I'm supposed near the vicinity of the reactor, where everything's closed down now. Then, so you could see that that's the phase transition from the iron core of an asteroid or something to where the soil is fused from the heat. And then you go to what's basically rock, but impregnated in is lots of little stones, little metallic stones. And you can see that from the shine, that's the iron little clumps in it. And then you go to a totally stony one like the AIAA that fell in Mexico. You can see it's made up of what called chondrules, little white things there, chondrules, and little balls that are stuck together. Now, if you take the iron one, an iron meteorite there, and you etch it, I have several samples, you put acid on it, you bring out the fact that it's crystalline. It's very interesting that these iron meteorites are actually crystalline growth. And that shows you the crystalline pattern called Widmanstätten pattern. And then there's something called tektites. And we got lots of those all around the earth, and they come in all sizes and shapes and colors, but they apparently have come back through the atmosphere. The supposition is that they're either from the moon or from the earth, primarily from the earth, they think. And you have a big meteor, a big asteroid hit the earth, and the dirt comes off and is vaporized, and it crystallizes and comes down as glass. This is a piece of glass. They can be perfectly clear, just like this one, only perfectly clear. They're beautiful. But they're called tektites. We're not quite sure, but they've obviously been through the atmosphere and have been abraded. So, whoops, dang it. This is the interplanetary meteoroid model that we developed at JPL. My close friend, now deceased, Neil Devine, developed this model. And it's still, as far as I know, pending the data from the Pluto mission, the only one that has measurements out to past Uranus and Neptune from the Voyagers and the Pioneers. We'll see that in a second. But JPL obviously is going out into the outer reaches of the solar system and in towards the sun. And we need accurate models for the meteoroid environments. It turns out at the sun, you can actually see the comets falling in and things like that and get an idea of after they go by what's left of the clouds and stuff. And you can actually see comets falling into the sun and get some idea of the meteoroid environment there. They're going upwards of 400 or 500 kilometers per second by the time they get to the sun. And that's basically nuclear weapons grade velocities for the energy that's associated with them. And they the last thing that goes is pretty much to carbon compounds. And so a lot of them are vaporized, the metals and everything vaporized long before that, but somewhere inside of about the 10th of AU, everything gets vaporized. Anyway, so we needed these for Galileo and Cassini. I did a lot of micrometeoroid studies on Galileo and Cassini. I did the micrometeoroid studies for those, and you'll see the programs I used and everything. And this was the model that we used. This is where you can get data from. The zodiacal lights. I've actually been on a field trip where we measured the zodiacal lights. And from those, you can get what size particles they scatter infrared light. You can figure out what they are. And they go into about 0.3 AU, around in towards Mercury's orbit. Helios, of course, went in that far, and we were able to measure impacts on that. And then you can see the size range. These are really small. They're milligram, smaller than the milligram. They're microgram particles or smaller, nanogram and picogram particles that you're seeing. And anyway, the interplanetary flux is measured roughly at 1 AU by whatever hits the Earth. You can walk out and pick up the pieces and figure out what size they were, or you can take pictures or use radar to measure them. JPL's Deep Space Network is always contributing measurements of meteoroid environment because they can see the meteor trails as they come in. Their plasma, and so their radio waves bounce off of them. And so we use those to measure the space debris and measure the entering micrometeoroids. they can see down to about 10 centimeters on the DSN. And anyway, so you can see Ulysses, Galileo, Pioneer 10 and 11, and Voyager. You can get some. Now, Neil divided the data up into 5 populations. He called the core, inclined, eccentric, halo, and asteroidal. These are very arbitrary, but we've tended to keep these in our new models. And this is what you're looking for. Just like for the plasmas, you need a you need a particle distribution function. The only difference between this and the plasma distribution functions is the HM and the G sub naught. G sub naught is basically the effects of the orbit. That includes the perigee and the inclination and eccentricity of the orbit. You can see that down there under 0.2. HM is the mass distribution. You have to add in these things depend only on mass, M, rather than we don't normally do energy, we do the mass and the velocity. And then of course you have your phase-space density function there. The number particles is equal to the HM times integrated over the mass, G naught, which contains the orbital data, and then dy dx, and then dv dy dvz, the velocities. And we typically integrate the phase-space density over the velocity, the 3-dimensional velocity, to get the number density and things like that. So this is what the functions look like. I'm sorry, I don't know why it keeps jumping. Anyway, this is what the distribution functions look like for each of the different components. Mark Matney at Johnson Spacecraft Center is the key person for space debris. And he took this model and cleaned it up a few years back and made it very useful for the community. He was able to change some of the ways that Neil did it. And anyway, this is the different distribution functions for our micrometeoroid model that's used at JPL. And as I say, both Johnson and has the debris models, and Marshall under Bill Cook has the MIM model. We have the METAM model. That's the meteoroid engineering model, and MIM is the version at NASA Marshall. It only goes out, as far as I know, to Mars. We are the only ones that go out beyond that right now. I know that the PI for the Pluto mission gave me hell about that, and he says he's going to update the model, but I haven't seen any results yet. And it's just atoms, yeah. Anyway, this is the model. You saw where the data came from, and we took that and turned it into a PC model that you can get. If you contact Martin Ratliff at JPL, you can get a copy of it that runs on a PC. And I think I have a copy of it too, but I've never run it. And this is what it looks like. Basically, you put your orbit into this, and it comes back out with the flux of particles as a function of distance from the sun. And that's, you're going to see in a moment, that's what we need to do micrometeoroid calculations. This is a comparison of the MIM and the METAM models at 1AU. Of course, 1AU, we have the best data, and so all the models should agree. And this is the key thing. You need two issues. You need to know the mass of the particle and its velocity and its density. And this is the annual fluence annual fluence versus the log of the mass of the particles. It's at 1 AU, and that's sort of a standard curve. Now, let me show you how you use all this stuff, how you use METAM or MIM or whatever other people are going to come up with. On the left are two orbits. One is 1 AU orbit, that's the Earth, and we have very good statistics there because we can see what's coming in and we can measure it in their backyard. And Helios went inside Mercury's orbit, and we were able to get measurements from that. But that's the Helios orbit that you're seeing there. And then Cassini. Cassini, as you know, bounced off several of the planets in the inner solar system, Venus and Earth, and then went out to Saturn. And this is its orbit. And you're going to see the effects of these different orbits on the fluxes. Now, here's the kicker. What we're looking at here is what the fluence, that is how many hits you would get as a function of day into mission. On the Helios fluence over here, remember you're going into the sun. And what you're seeing is most of the gunk that you get hit with is coming from behind you. And then when you go out, you're not getting hit. But so as you come in, you can see that the dashed line is the stuff hitting you in the butt. And you're not getting the dotted line down there is the stuff you're hitting on your nose. So it turns out that there's a big difference between the butt and the nose. Now at Earth, you're going around. And so you're getting stuff from both sides. And so what we normally do for Earth orbit is we assume a randomly oriented satellite, and that gives the most fluence. And you can see that the stuff going in towards the sun, again, is what dominates, and the stuff going back out from the sun. And the right one is the interesting one, because with Cassini, it went in and then it went out. And so you can see when it went in, the stuff hitting it in the butt went up, and the stuff hitting it from the front side went down. But then when it got to that point where it was heading out towards Saturn, everything's hitting it in the front. So what I'm trying to tell you is that if you're flying a spacecraft and you're worried about micrometeoroid impacts, which we were on Cassini, by the way, and what you will see is that the things going out get hit in the front, things going in get hit in the butt, and things going around the Earth get hit from all around from the sides. And so that's an interesting interesting statement from that. Now notice that I used 1 gram as the discriminator for mass. I integrated basically from 1 gram up in size, and I'll show you how you do that in a second. Now, here for reference is what the Helios, the 1 AU, and the Cassini fluxes look like. They're based obviously on days, and so how long the mission lasted. 1 AU, we just took 365 arbitrary, but you can see all the different codes. There's official NASA, there's a Galileo model, there's an, I forget what APROB stands for. Anyway, and METM, and you can see all of them are kind of in the ballpark. Cassini was just used the APROB model, but you get the idea. And then you can get the fluence down there there's 2 different ways I did this calculation. One is I integrated from 1 gram up for the distribution function. MC, I determined at any given point what's the critical mass was that would cause penetration of I believe it was 100 mil surface. And that, since that's the standard reference. And so for 1 mil and 100 mils and that critical mass, we got these values, okay? So there's 2 different ways you can figure a mission. You can figure for the critical mass that whatever your mission will tolerate, depending on how thick your shielding is. You pick that shielding and you trade that off with the mass and the velocity, and you get a critical mass that'll penetrate, and then you integrate up from that critical mass to get the total number of particles that are hitting you. Now, here's what you might be interested in. We did this, my colleague Robin Evans did this for a paper that we did for the official Mars meteoroid mission model. And the left over here, you have things broken out by segment. We used a Hohmann transfer orbit to get to Mars, stayed on Mars for a year, and then we came back when when we could go on a Hohmann transfer orbit. You remember Hohmann transfer orbit's the most efficient way to go back and forth between Mars and Earth. Anyway, there's the different segments. And so you can see what, as a function of meteorite mass, what the total fluence was for a Mars mission. And you can see the total mission fluence there. Now, if you go over to the right, now this becomes very interesting, because what you can do is break it out by velocity. And so these are velocity bins. 40 kilometers to infinity is the blue one at the bottom, and the pink one is the total. It should agree with the one on the left. And you can see typically 25 to 30 kilometers is one of the, let's see, which one is the worst one? I guess it's, okay, 0 to 10, 10 to 15, and 10 to 25. Anyway, that gives you an idea by velocity bin. And so you need to know how many are in a given velocity bin, and you can calculate how much damage it's going to do. By the way, I did this for solar sails, and it turns out even for a huge solar sail, the amount of damage done because of sunlight, believe it or not, it turns out that the sun's photon pressure pushes all the stuff below about a microgram or something out of the solar system because of solar pressure. And so this turns out that the flux of particles drops off dramatically, as we'll see in a little bit, with size. And so since you have lots and lots of small particles, they're getting pushed out by the sunlight, so you don't have that to worry about destroying your surface, because the little particles will do as much damage as the big particles. And so it falls off, and it turns out it's only a small percentage of a solar sail will actually be damaged by micrometeoroids. Now, here's a kicker. And you know, I mentioned Mariner 4. It turns out we believe it went through a meteor stream. So JPL has ever since kept very detailed models, and this is only a small fraction of meteor streams. And we try deliberately to steer away from meteor streams. The worst one, of course, was the Leonid stream. If you remember back then, about 20 years ago, they were really worried about that. And Mars also got hit with a meteor stream recently. And they basically, what people do is they try to orient their satellites so they don't get as many impacts. And then they try to try to put more people on. So if they get hit, what they typically you'll see when you get by a meteoroid is you'll see the satellite start to tumble. And so it depends on how fast you can recover it and from tumble or starting to mutate. And so one of the big things they do is they put a lot of extra people on during the passage to a meteor stream. But anyway, I thought you'd find it interesting that we worry about meteor streams. And now the other thing we worry about is rings. It turns out that Jupiter, Saturn, Uranus, and Neptune have rings around them. And I'll give you a list of those at the end where you can find them. Anyway, this shows the rings of Saturn and the rings of Jupiter. And sure enough, they affect the radiation belts. The particles absorb the radiation belts. And at the same time, they can see on antennas the microparticles clobbering the antenna. And you can hear the RF noise from the impacts. And so we can detect them. This is comparing the mission totals for the Saturn ring passage versus the total mission to Saturn. And here we assumed an average velocity of 15 to 23 kilometers per second. And the big thing that you have to assume is what's the density of the particle. You know, you'd think it might be water. Well, that's 1 gram per cubic centimeter. 2.5 is what we usually take canonically. But then again, you can put any value in because look, you have iron meteorites. Iron meteorites, I think, is probably about 1 in 20 or 30, if I remember, once it hit the Earth. But the bottom line is that they're 8.5 grams per cubic centimeter. And so we're getting ready to fly to an iron asteroid. There may be chunks of iron floating around it. So you have to be careful about how you do it. And remember that we've flown through comet tails and stuff, and we have seen particles hitting them. The Europeans saw a lot of mess whenever they have little volcanoes on comets, and people have calculated the velocity of those things streaming out and hitting the vehicle. And I was asked to worry about how much dust was coming out of a comet and whether it would coat the RTG and fins, and so they would overheat. And we actually did a detailed study of the rate at which dust accumulate on fins from micrometeoroids. Whoops, dang it, I'm sorry, it's really frustrating. I hit the button and it goes 2 slides. Anyway, this is the other problem. How many of you remember Sanford and Son? I actually heard him when I was in the military. in Montgomery, Alabama, he came down and gave a show for us. Old Sanford, Red, I forget his last name. Anyway, that was a very popular television show in its time. And he basically was a junk collector. But you get the idea. And I don't know if you can read the title on the other one, How to Tell When Man Has Officially Conquered Space. He's dumping all this stuff at it. And it's as bad as you can imagine. You know that they used to flush the commode on this shuttle overboard? And they have beautiful pictures of these 5 to 10 kilometer long comet tail coming out of the shuttle when they flushed it. It's just beautiful. I have pictures of all the chunks of ice floating around on it. And in fact, I hate to say this, but they brought back some samples from a satellite they recovered using the shuttle. And they found what they were able to identify as frozen urine pits in the side of the satellite. So anyway, I digress. But this is, you saw the effects on from spacecraft charging. Well, you also have the same thing from micrometeoroid impacts. These are believed to be, they don't know for sure. I think they actually do know, but I don't remember what the result was. These are debris or micrometeoroid impacts. MMOD stands for micrometeoroid orbital debris holes. And you can see all the little pits and stuff on there. And what happens is they'll crack the glass and short the solar array out. It's a real problem. And this is from ISS. These are samples they brought back. And they've even had problems with the astronauts outside moving their hand along the guide rails that they hold on to and running up against the micrometeoroid pit with a sharp edge that could possibly cut their hand glove, cut their glove. They've had some problems with that. Anyway, this is this gives you some idea of what orbital debris looks like. It's much worse now, by the way. And there's sites that you can go to, and they'll show you the instantaneous distribution of debris, junk in space, all the pieces and stuff. But the big thing is, notice that payloads is 31%, and rocket bodies. Those are the dangerous things because they're dead, they're floating around, and even my Clementine, we launched the second to the last Titan II to go to the moon, and I failed to do the debris study for it, and damned if our tanks didn't blow up, and we became like the 4th or 5th worst debris generator for space debris at the time. It's embarrassing when you know this stuff and you forget to do it. But no, Mark Matney and J.C. Liu are the experts at NASA Johnson that you need to contact. And that used to be the home ground for Don Kessler. who was basically one of the founding fathers of the debris. But this is gives you some idea of the distribution. Notice that around the Earth in Leo, there's a tremendous amount of gunk. Whereas you look on the left up there, you can see the geo environment. You can see where all the stuff is in debris. So what they're starting to do for Leo now, and I participate in some of these, they're going to fly up modules that will plug into the satellite and then deorbit it. And we were working with, was it SAIC? I'm trying to remember who it was now. Anyway, we did a study of where we combine spacecraft charging and debris. They were worried about when they mated with the satellite, there would be a big arc discharge. So we helped them do the test and stuff. And I told you before, you spray it with a neutral plasma and all your problems go away. So that's what they ended up doing. And they did, they were able to mate with a vehicle and add fuel to it. So that's the next big thing is people are designing these vehicles to go up and mate with the space debris and either make the thing work again or bring it down. This is the distributions. Now, if you're looking out the front of your vehicle and down is the Earth, and you look out the front, the left picture up there is the angle at which things are going to hit you. They don't come much from up above you or below you. They come from the two sides at about 45 degrees in front of you. And that's because there's not much in your orbit, but there's going to be stuff that's coming in at slight angles to you. So that's what it looks like. And you can get hit from the butt if you look here, but typically you're going to get hit from space debris from the front direction, and the velocity is going to be about 7 to 10 kilometers per second. And then on the right, you can see the latitude distributions. Those are Molniya orbits, for example. And the big one over to the right is, of course, the launches from Kennedy, places like that. And then you see the polar ones are the ones from Vandenberg over there on the left. But this is the latitude distribution. And so then you can see a cut at the altitude distribution. You'll see a slightly different curve in a minute. And then, of course, the distribution on the left reminds you where things are. So it's out at geosynchronous, and it's at Leo, and then the GPS orbits in there in the middle, I think. But here's the big kicker. Don Kessler, and I actually was the person who published this paper in my first space environments book for AIAA. What he published was he took a study where he put all the junk in orbit at the time, and then he ran it forward in time, and he made some assumptions about what happens if things collide. And he found out that if it's 320 objects per year over on the right there, which is probably close to what it seems to have worked out with, you would see 1 or 2 hits per year where the things would run into each other. But notice that the curve goes exponential, particularly at 13% growth rate per year curve. What's happening is you're getting a cascading effect. One satellite hits the satellite, and they put out a bunch of debris. That debris runs and hits other satellites, and then you get a cascading effect, and you get what's called the Kessler syndrome. You get catastrophic decay of all the objects in Leo, and it just disintegrates. And this was his original assumptions. And you can see that the first known satellite collision was with Iridium 33 and Cosmos 225. Cosmos was dead, Iridium was active, and that occurred in 2009. So one of his curves sort of fits, the 320 object fits, but it's a real problem. There are now international standards. We have to, for every mission that we plan, we have to show that for Earth orbit, we have to show when it'll die. There are certain parking orbits where you can park things if you can't get down, but you're supposed to leave enough fuel to burn yourself up here in Leo. And then, like I say, there's parking orbits out at GEO where you can move the things out of the GEO regime. Because you can imagine what happens if someone, God forbid, goes out and fires a spacecraft in the opposite direction to the way GEO orbit is, which is counterclockwise, and you fire something in that direction, you could fly a can of paint and blow it up, and the little particles would probably be enough to cause significant damage to the geosynchronous orbit. And my favorite one was we did an analysis where people were going to use mercury droplets. They would send the mercury droplets out in a big fan and catch them. And that way, because they were little bitty droplets, they'd radiate heat about much better. So they'd have like a 20 or 30 foot catchment, and then they'd shoot from a little gun, shoot the particles out. They would radiate very much more efficiently, and then you catch them and recycle them. And we were able to nix that one. Can you imagine if it failed, all those mercury pellets? It turns out that back in the early days of the space program, there's a Project Haystack. They flew a huge amount of little needles, and they were going to use the needles spread out in orbit to reflect radio waves. So they didn't need the communication satellite, they just reflect off the needles. Fortunately for everybody concerned, they had them mounted in wax. The wax did not evaporate efficiently, and so they stayed clumped together. But can you imagine thousands of little centimeter size little wires floating around in orbit in LEO? It would have been a total disaster. But anyway, we got by that one. So bottom line is satellites are running into each other, and this shows you the actual spectrum. If you notice, it starts to flatten out below 0.00001 centimeters over here. It actually goes down to a little further to the left, thank God, because of the photon pressure. But the main curve here is the meteoroid curve. That's to the left. Above 1 centimeter, mainly going towards 10 centimeters, that's all space debris now. So that gives you some idea of what space debris is doing to the ambient natural meteoroid environment. I might add, though, that we actually get stuff, anything going over 70 kilometers per second is from interstellar space. And we get a number of 70 kilometer per second pieces coming at us. So it's entirely possible that there could be some chunk with our name on it out there coming towards us. I'll warn you. I have the curves for that too, because I've done interstellar missions. We've done the micrometeorite counts. Whoops. There. 3 tries is a charm. Now we're going to start going into actually how you calculate the impacts. We've seen the environments. That's what we just finished up with. Now we're going to go see what they do. Okay, this is what you're going to be looking at. This is an actual shield brought back from, I believe it was Solar Max mission, where the space shuttle recovered it. And what you're seeing here is the front surface is on the left. Notice that the scale is 100 microns, that little bar. And down on the left, down the right there, that's 1,000 microns. So there's a 10-to-1 ratio between the front shield size picture and the rear surface. Now, what the idea is Fred Whipple came up with the idea during, I guess, maybe in the Second World War, that you use the front shield to break up the particle. And the particle becomes pieces. They expand in a spherical shell, and then they hit the back surface, and they're a lot smaller and moving slower. And so you put your main shield back there. So you use a sacrificial shield up front. You break up the particle, and that stuff then rains down onto the rear surface and doesn't cause anywhere near the damage that the single particle would do. So that's called a Whipple shield, and we'll see how that works. Now, before we go any farther, you can see a picture up here. In this case, the particle came from the left and went to the right. And this is the way the shield is supposed to work. And we're going to see a movie of this in just a second. But the particle comes in, it hits, there's backscatter, that's the stuff to the left. And the stuff is reflected out from the crater. And then you penetrate, and then everything on that side is supposedly vaporized or liquefied. And it expands outward with 1/r² as you approach the back of the shield. Now, all that works good, but there are lots of ways you can defeat things. That's one way. You penetrate. So penetrate, you can break a xenon tank breach. Spacecraft module might be penetrated by a piece large enough to damage internal electronics. And there, my friends, is why you do not want to put two identical circuits, one being redundant to the other, next to each other. Because if you're getting taken out by a expanding meteor shell of particles coming at you, it's going to take the other one right out if it's anywhere nearby. So you want to actually physically move pieces apart so that when your meteoroid comes in, it doesn't take everything out. You can see, for example, radiators, breach of coolant loop, surface damage, paint chipping, and solar array arcs. You've already seen the solar array arcs. Now let's look at the paint chipping. Look at the left over there. At the lower left, you see a picture I took of the Wide Field Planetary Camera outer skin that came back from the Hubble when they recovered the JPL Wide Field camera. Now look very carefully. That thing's about 4 feet by about 2 feet. It's the size that you're looking at there. And the surface had, I think, if I remember, you can see it at the Smithsonian, the very item. And there are lots of little holes drilled into it because they cut out all the micrometeor holes. There's something like 600 of them in it after about a 5 to 10 year mission up there. But this is what's weird. If you look at the thing on the lower left, you see a little crater in the middle. I hope you can see that. That's the actual hit. That's the impact. Now, what happened was a shock wave goes out from when you get an impact. In paint, it propagates along the surface and it shatters the paint. Now, there'll be about 5 or 6 for every one of these little crater things. Dark rings around each one of the little micrometeorite pits. With time and thermal aging, the paint comes off and it just falls apart from thermal cycling. And so what you get is a little crater and a huge bout of paint chipped off in the middle. And I think I've got a lot of pictures of those. I thought those were kind of neat. It turns out every surface interacts in a different way. Glass, of course, chips. I don't know if you've seen the hole in the space shuttle window, but there's a big chip in the window right when one of the astronauts was looking at it. Fortunately, they were like 2 inches thick, so it didn't kill him. But anyway, you have to work through for every surface and every thing inside the spacecraft what the failure mechanism is. We'll see this in a second. Let me see. I think it's the next one. Nope. It's coming up. But this is what happens when you get a crater. Burton Kerpoulet at NASA Johnson did a whole bunch of studies. Initially, they started out with basically what's an infinite surface, and they collided particles up to about, well, you can see a little over 10 kilometers per second in the surface. And then they measured versus the particle size versus the pit size. DC is the penetration depth, DM is the particle diameter. And down at the bottom, that's the relationship between the DC and the DM, between the crater size and the meteor particle as a function of velocity. Okay, notice that the velocity is to the 2/3 power and the density to the 1/3 power. And I'm now going to show you how you derive that. That's the empirical formula, is the thing on the bottom that he measured. That's the straight line you see up in the curve. This is what happens. Let's start out. We're going to assume that the energy that of the particle hitting is 1/2 mv squared. And of course, you need the volume, so that's the diameter of the particle divided by 2, so it's 4/3 pi r cubed times the density over times the velocity squared over 2. 1/2 mv squared, okay? That's what's coming in to hit you. Now, we're going to assume that there's a thing called the constant of the material, and it's the heat proportional to the heat of fusion. Is what is how much energy it takes as a function of the density of to vaporize or liquefy the material, depending on how you want to do it. And so what we have here is we have the mass of the crater is half a sphere. You've seen craters, you know they're basically half of a sphere. So that's 4/3 pi r cubed again, times the density of the material. That's how much the mass of the crater is going to be ejected. And then for that, we need to know the incoming energy, and the ratio of that is some constant times the density. So you can see the second, if you take the equation on the right and you push EM into it and you ratio that side with the complicated thing on the left there, you could get the following equation. dc, the depth of the crater, is equal to this constant, which is dependent on the material, times the diameter of the meteoroid, times the density of the meteoroid, times the velocity of the meteoroid squared to the 1/3 power. Okay, now let's go back. Ta-da! Same problem, same formula. Okay, and it agrees with experiment. The kicker here is the velocity and the material properties. You have to determine every material is different. And the big thing here, let me see what's coming up next. All right, this is the deal. You can have a really thin shield, and the meteoroid just comes in cookie cutters, goes right through, cuts out some mass. It actually makes things a little worse because you got more mass coming in. And then you can see the other situation is, how do we actually figure a failure? Well, the particle hits, and if it's a fairly thick shield, think what happens. A shock wave goes out. That shock wave hits the back surface of the shield and keeps going. Unfortunately, it also reflects. So you get a shock wave that, because it's changing the index of refraction, or speed of sound actually in the material, the shock wave reflects off the back surface and comes back towards you. And at the same time, the shock wave itself is still propagating outwards. So what happens? You rip off a chunk of material. And if you've seen glass when you hit it with a BB gun, you got a little hole in the front, and then you got an hourglass shape coming out the back. That's because of what we call spall. The spall is created because the shock wave is reflected and continues on. Some of the shock wave energy is reflected, and because it goes straight on, and it basically tears out the material. And so the question is, what will fail your satellite? If it's a tank, for example, you really don't want it to make a hole all the way through. So what you have to do is you have to calculate for the minimum size impacting particle when the small hole necks up to it, sort of like an hourglass. Picture an hourglass, and if it just touches and there's a hole there, then you're going to lose gas and you're going to leak. So that's one issue. The other one is that the spall coming off is going to cause you problems too. So anyway, Swift, Bamford, and Shin made some calculations, and they came up with this theoretical formula. The AIAA actually doing the experiment came up with the following formula down there. They're related, but you can see they're not quite the same. And it turns out that there are like about 30 I collected about 30 or 40 of these formulas. The people at AFRL have a book of just nothing but people's calculations of these formulas that they gave me when I worked there. And it's incredible. Everybody comes up with their own formula because it's very dependent on the material, as you can imagine. So now watch this. If you look at the lower right over here, you can see what's being 6.7 kilometers per second, the 6 millimeter stainless steel projectile. And the bumper plate, you can see, here's the little particle it hits. You can see the backscatter, and you can see the big 1/r² thing in the front. And then you can see how most of that stuff's trapped between the two. So this is what you're trying to do with a Whipple shield. You're trying to break up the particle. And you spread it out over a large area and reduce the mass coming through. I love this picture. That's your satellite. That's your satellite on micrometeoroids or space debris. Because hopefully you got the idea. We can come back to that if you want to talk about it. All right. Now this is the Whipple shield calculation that people have come up with. The difference between this and the single surface just crater, the single surface, just make a hole through it with the spall, or this. This is where the spacing becomes important. Remember in the previous slide, you saw how the thing expands. Remember, there it goes. See it expand? 1/r². So S is the spacing. And so on the space shuttle, a space station, I believe, I think they're spaced off as much as a meter from the actual crew cabin and stuff. They have these shields on it. And this is the bumper. TC is the thickness of the front shield as a function of the momentum of the incoming particle over the distance. And then there's this what we call non-optimum. I'll describe that in just a second. So, oops. Okay, let's go. RL is the density of the shield as opposed to the density of the meteoroid. Those two equations don't really look the same, and they're not supposed to. This is the issue. If you shoot something at a shield, if the shield is too thin, the shield will totally melt. That's the lower shaded region down here. Aluminum shield melts. And you can see that as the thickness of the shield goes up and as the density of the shield goes up, the velocity has to go up. Vice versa, if you want the stuff to melt, you have to, the aluminum projectile melts, you want the shield to be thick enough that it melts it. And you can see there that is inversely proportional to the velocity and mass, the thickness of the shield. See how aluminum projectile melts? That's the region where it melts. Anything that's above that velocity will melt the projectile. And from like 10 kilometers, you can see it goes all the way up from about 0.1 for the ratio. And as you get to thicker and thicker shields on the left, as you get to thinner and thinner shields on no, I'm saying it wrong. The velocity goes below 5 kilometers per second. The thing goes up that you have to have a really thick shield to make it melt. So anyway, on the right, I've done a calculation where I calculated the results of a single wall. You saw that was the early calculations we did where you just penetrate. And I did one for when you do the Whipple shield in the optimum range. That's the optimum shielding, and that's where the projectile melts and the shield melts. You want them both to melt or gasify. Otherwise, you're going to have problems. And so then I've shown the non-optimum solution. Notice that you can protect against a mass almost 3 orders of magnitude higher. Okay, that's the reason we go to Whipple shields. That's why tanks use Whipple shields. Is because you can get a 3 orders of magnitude increase. Unfortunately, you can also, if you're not in the optimum range, you can make things worse. So you have to be careful. And that's it. That's the calculations for determining the critical penetration mass. Now, I'm going to go through this moderately fast. If you want to ask questions on it later, please do. But this is the process by which we calculate whether or not a spacecraft will be significantly damaged by micrometeoroids. First thing we do is we determine the critical mass. That's the mass at which failure will occur for the specific system. You'll see that we group things in all kinds of different types of effects, particularly for the space station. They have all sorts of different ways you can fail a given system. So each one of those, the critical mass is different. It's a different velocity and angle and such. All right, that's the G function. Now what we're going to do is for the mission trajectory, we're going to calculate what the flux is. Flux is the particles per second hitting you. And in particular, we're going to determine it for the critical mass. And you can see that the time is in there, because when you integrate over time, you get the fluence. So you get the whole mission fluence. Now, what we then do is we take for the flux of the function of time that will actually fail our system for a given system, we integrate over the velocity space. That's the dv, the dv there, and over angle and mass. Now we start with the mass because we want to know what the critical mass is. That MC is a function. We plug the function in there and vary it over whatever you need to get the critical mass that fail it. So that gives you the flux. And it looks complicated. It is complicated, but it's straightforward to do it. Then what you do is you integrate, if you want to know for the mission or mission segment, you integrate between T1 and T2 to find out what the total fluence will be that will fail your spacecraft. And then fluence is per unit area, so then you multiply by the area, and that tells you what your actual probability. And that's what the next step is. Here's what we do. The probability of X meteoroid impacts in a given time interval is very small, as you can imagine. Therefore, it follows what's called Poissonian probability distribution. That's the probability there, probability of X meteoroid impacts in a time t. And that's the Poissonian probability function. We know that that's the flux there. Fluence, I'm sorry, that's the fluence. And AC is the area. And X is the probability of number of impacts, say 20 impacts or something in a given time interval. So that's what you can calculate that. Now, that's not that particularly easy to calculate. So we use a trick at this point. The trick is we assume there's no impact. That says X equals 0. And guess what? The probability function becomes very simple. It becomes just an exponential of the flux, the fluence times the area. It's for that. And you can expand that to 1 minus the fluence. Since that's a small number, you're going to expand that again, and you get 1 minus the fluence that you're not going to get hit. So the probability of no impact is the total probability minus the total fluence times the area. That's a probability you're not going to get hit, okay? So the probability of one or more impacts, because that's all you're worrying about. You want to know if you're going to get hit at all, where X can equal 1, 2, 3, whatever, is then estimated by X, anything greater than 0. Any impact that's critical will fail you in a time interval. And there you go. It's simple. You subtract the probability of no hits from the probability of all hits, and you get the fact that critical fluence times the area, surface area, gives you the probability of being hit. And that should be obvious anyway. And so sum over all time intervals to get the total emission fluence failure probability. And that's what's shown in the last equation. Hopefully that's clear. We can discuss that if it's not clear to you in a little bit. Now here it is for the entire ISS. This is Mark Matney did and J.C. Liu did this calculation. That's for all the different modules, particularly the ones, the habitat modules, the lab modules, and so forth. The probability of no impact, remember, that's what we calculate. And so the odds of an impact subtracted from 1 is that. And then you can see the probability of no penetration risk from debris. There's two different things of calculating it. They come out about the same, but odds. So that's the risk of from 1 millimeter debris and debris penetration risk for everything. So there you go. And so its odds to impact are 1 in 15 on the space station, or 1 in 146. And you would be surprised to know that the Russians claim that they have a hole in their module. And they've been having problems. They had one of the, I remember one of the Soyuz capsules got holed, and they had to jettison it. So, and like I said, the windows get cracked, everything. So there you go. That's how you do it. Now, what are the issues with hypervelocity impacts that we need to consider? Right now, above 10 kilometers per second, we really have very little experimental data. You can get above 10 kilometers per second, but it's very expensive. You have to go to one of the nuclear fusion facilities and ask them to bounce a particle off the wall. And there's no telling if you'll hit it, the spot you're interested in. But they claim they can do it. They actually proposed to us that they could do that for us to get up to the 400 kilometers per second. Near solar, cometary, and Jovian meteoroid environments are not well defined at this time. They're getting better, and with the solar probe, we should get a lot more information. And people are continuing to map the comets as they come in and get an idea. But and we also have Juno right now. And you can, as I said, you can use the antennas to measure the really small stuff. It's the bigger stuff that's your problem is. Meteor streams are a growing threat to Earth's constellations. There was a big study on the Leonids. People were totally panicked. And like I say, they closed their solar arrays up, folded them up, and did a bunch of crazy things. They didn't have much problem. They did see stuff for one of the Martian intercepts of a meteor stream. The process of determining meteoroid effects on RTGs is a major concern because obviously in the outer solar system, you don't know the environment and you don't know the RTGs. Let me tell you what I did cause another problem. On Cassini, if you ever go to the Los Angeles Science Museum, you'll see the Cassini satellite up there. And what you will see that's not in the pictures of the satellite anywhere else is a little dome over the engine. There's a rubber baby buggy bumper, the baby buggy bumper that goes closed on the engine because my calculations showed that the micrometeoroid environment on the way to Saturn was sufficient to cause a penetration of the main engine cone, and it's a disilicide layer. It only had to penetrate a few microns, and when they turned it on, that would melt the neodymium thruster cone. So I was able to show. We flew Clementine with a broken, the same thruster, and we had a crack in it. It was 4 inches long, and we didn't have a problem. So I kept telling them, the Galileo project, that they didn't really have a problem because I knew that even the penetrating with a micrometer wouldn't do it. But they were so worried about my calculations that they put that dome on the engine. The only time that dome is open is when they're firing the thruster to go into orbit and do those things. And so if you ever see it, think of me when you see the little bubble on covering up the engine. And need to evaluate the effects and impact to use plasmas and EMI on spacecraft systems. As I've been discussing, the plasma bursts can short out solar arrays. The EMI makes noise on various instruments, and it's just a pain in the butt. Space debris control is an international concern and is growing. It's becoming a major issue. The United Nations has taken it up, and the Kessler syndrome is actually a reasonable, well-founded concern, and people are very concerned about it. And finally, we need to be able to do believable tests. We can hardly get over 10 kilometers per second, and that's just, it's agony. But again, it's very expensive. You fire these, some of these guns are 20, 30 feet long, and you have to rifle the whole bloody thing. And you fire a bullet and it melts it. So sometimes we get it wrong. I don't know if you know what happened with Mars Climate Orbiter, but JPL did all its calculations in metric. The contractor did all their calculations in normal feet, inches. And the net result was there actually was some fights over this. The two teams got together and got really mad about this. So, like I said before, an ounce of prevention is worth a kilogram of cure. That pretty much sends it. I have included a bunch of selected references from my own work. You can find, for example, the Space System Interactions, Earth Space Environment, AIAA Press. That's an 800-page book with the first conference that we ever had on space environment effects. And there's some nice chapters in there, like how you can pollute the Earth's environment by trying to put solar array farms in geosynchronous orbit. And the people stomping around on the moon are going to cause enough atmosphere that it'll screw up the observations on the far side of the moon. And so anyway, there are lots of interesting papers in there. If it's old, but it's not wrong. And the things in blue are my books, if you're interested. And I did do some of the first measurements at the lunar surface back in 1971. I measured the plasma sheet there, and that's still valid. And I have about 160 publications at this point. So that's about it. There's one last thing. If you write me and you're really nice, since it's going to cost about $2 to mail it, I have this poster. It's about a 3 foot, 2.5 by 3 foot poster. On the back side are all the environments and that go with the diagrams. And it has the ring, all the ring measurements and all that stuff. Anyway, it's a JPL poster. I have a few copies I could send out if you don't ask for more than one or two. And let me know. You have my name in the front and address, and I'd be glad to send one out to anybody that wants one. I've got about 20 or 30 left. We printed 30,000, so we did pretty well. And that's about it. I'm done, Ken. You still there?
Yeah, yes.
I'm afraid everybody went to sleep.
No, that's so exciting. How can I sleep? So many, So you want to take question now?
Yeah, I can take questions now. And I was going to say, I want to point out that all the stuff you see on this view graph is available online. You can study, everything is online. JPL has a complete database where you can run the interplanetary environments if you need them I think they even have the micrometeorite model working on there. All the contours you see, everything is available. You can do the radiation calculations for a given mission. You can do, I think you can do the micrometeorite. I don't remember if we included that or not. But those are the two biggies, by the way. And for these, you can do things. My other talks are going to be involved with atomic oxygen and atmospheric physics and stuff like that. I'll probably be giving at least one more. This, by the way, is a 2-day course that I've taught many times since 1984, I guess.
We can do it. We can do it 2 days, 3 days, whatever you want. Gary and I will be.
Well, I'll be honest with you, I'm worn out. I turned 76 in February, and this is harder than I thought it would be. I used to do 2 days at a stint.
Oh, we can break it down. We can break it down so to make it easy.
So, questions?
Question. Oh, before question, I want to first mention Gary here. You mentioned he's actually our technical chair. Generally, Gary busy Saturdays. With the Wright Flyer replica event project. He can tell you a little more about it. Well, hopefully in the future he can lead and moderate this series. This is a very good technical event. He has been busy with the Wright Flyer, but I'm so glad he showed up today. Yeah, Gary. So Gary, you have a question? Go ahead. Or you want to say a few words or something?
No immediate questions. A 1-minute dump on the Wright Flyer project. The Wright Flyer project was created by the Los Angeles section of AIAA, and it occurred when the replica that was built in 1953 by the IAS was destroyed by a arson fire at the San Diego Air and Space Museum in the late 70s. And we decided to replace that aircraft. And in the course of that, we decided to produce a wind tunnel model that could be tested in a large-scale antenna air wind tunnel, which we did in 1999 at the NASA Ames facility, the 40 by 80. And from that, we wanted to build a flyable replica with significant changes to make it more modern and more capable, but maintaining the same configuration. And that aircraft is now out at near Riverside, and it's stymied by the fact that we are no longer trying to fly over sand or a lake bed, so the airworthiness certificate is an issue. Anyway, that project has now received a very generous donor who is wanting to go straight from the existing configuration to a museum display, skipping the flight test. And so I'm suggesting that we should make an award for the combination of that group. For all the effort that's been put on in all these years. And that's just basically the data dump. Anybody wants to go out to Riverside with me, then I'll do what they call a $100 hamburger, a ride out there and a cheap hamburger for a day. And that's basically the data dump.
All right, thank you, Gary. First, Dr. Garrett, can you turn on your camera because it's a Q&A. People might want to see your face. And secondly, maybe you can stop sharing because that will make your screen, your face larger on the screen.
There was
Okay,
a
now.
reason I didn't want to. They see me with my phone.
Oh, you cannot hide now.
Let me see. Is that better?
Yeah, it's much better. Any question here? If not, I'm going to ask the first question. So you mentioned about Whipple shield and the atomic model, but practically, it seems that on the space station, it has multiple layers, not just two layers. So how do you take, in fact, how many layers really needed? And then you also show the colorful modeling from the gentleman from JSC, that a colorful distribution of the effect. And is that you have different layers, number of layers on different part of different layer part of the space station. And also, right here in California, in Hawthorne and Long Beach, there's a new company called Vast Space. They are building the commercial space station habitat. The first one is called Heaven One. It's a very interesting name. So are they, and also Axiom Space, they are building the space station too. So are they taking this into account, building Whipple Shield for their new space station?
I honestly, I don't know. I haven't done it. But the bottom line is that yes, you need to take that into account. And yes, they're very complex surfaces. I don't know if you looked very carefully at the picture that we had of the space station, but they have many surfaces and they do very careful calculations of all those different combinations. We have some very sophisticated codes that allow you to calculate the effects. The problem is that you have to have the material properties for each layer to do a really good job. And that's where things get tricky, is being able to get the material properties. And the bottom line is that it's hard to do tests much above 6 kilometers per second. 10 kilometers per second is really once in a month or something, I think. They have a facility up at not Lewis, but at Ames, and that we use, and they have a facility at, there used to be one at Johnson. I don't know if they still have it. And then there's one out at White Sands. And there's been big fights over the test facilities in the past. But so you have to do testing. There's no ifs, ands, or buts to try to verify your models, because the theoretical models, as you saw from the strange equations that people came up with, are not overly applicable.
Okay, I see John, Mr. Reza, raise hand. So go ahead, John.
Yeah, my question, maybe this is addressed for a different discipline, but basically, I've done a little bit of studying on the effects of anthropogenic space debris entering the stratosphere or the atmosphere, and that the potential polluting effects or detrimental effects to the stratosphere or the ozone layer of these objects entering, even though we have natural space debris for millennium or millions of years, entering the composition of satellites and spacecrafts entering the atmosphere, especially with so many tons coming down in the future years. Is there a way that why are people not studying that or seeing the detrimental effects?
They are. I've seen some papers on it, but the biggest issue is the rockets taking off. And they put, I don't know if you know this, but the solid propellant rockets put out aluminum oxide particles, thousands of pounds of them when they go up. And they actually I have in one of my other talks, I actually show where they created a hole in the ionosphere from the water dump that they did from the Skylab launch. Skylab knocked a huge hole in the ionosphere, just neutralized everything. And so both ways, launches and things coming back in. And I have seen papers on that. I don't know if I could find the reference for you right now, but I do remember seeing that. And people are worried about that. And what the bottom line is, I think that you also need to take into account the stuff going up. The rocket engines and stuff dump a lot of garbage in the atmosphere. And
yeah, so no, those are good points in terms of going up. It's there's just less less applicable now to stop that. Whereas we could enter into a phase where we don't allow any of the anthropogenic space debris to come back in. Therefore, I say, why are you dumping it into the atmosphere? You're losing all its value. It has value there as a junk. We can need a junkyard orbit to do that, and that would commoditize and monetize the space debris. So I think there is an answer for that. As for vertical launching, yes, that's maybe something that time has come. We need to find other ways to get to space besides vertical launching, which it seems extremely wasteful, even though it's extremely effective and has become very cheap. Whereas there are other ways to do that. Virgin Galactic, of course, is helping with that, and other balloons and lighter than air vehicles potentially using that. So we're not burning so much up. But thank you for pointing out the vertical launcher, the going up, is a problem.
You'll appreciate this. One of my friends calculated what a space station like an L5, the big stellar communities in space, would do. And he calculated that just given what normally opening an airlock, air would leak out. And he said that within about 5 or 10 years of putting up a space community at the L1 point or something near the Earth, it would cause such a cloud to be created that the solar wind would be deviated from the Earth. And did similar calculation. Yeah, get my AIAA book. Anyway, he did a bunch of calculations like that. And the other one was, it turns out that if you want to go to solar power satellites, they would build them in low Earth orbit because the radiation is lower. People can get there easily. And then they would move them slowly using ion engines out to geosynchronous orbit where they would be placed. And the amount of plasma, the argon would be the gas of choice. Amount of argon that would be jettisoned would again totally would change the upper reaches of the magnetosphere from hydrogen and oxygen dominated to argon dominated. And we don't have any idea what that effect would be. So people have looked at, actually are looking at these things. Rich van Drack is a name you should look up. He's done a lot of this stuff, particularly on the lunar contamination. I wasn't kidding when they said that they calculated if you get boots on the moon that they'll kick up enough dust to screw up the backside of the moon.
Thank you for that.
Okay, I saw Bob, he made some comments on in the chat. So Bob, do you want to speak out?
You need me to, how do I get to the chat?
Oh, can you see the chat?
I probably can. How do I do it?
It's at the bottom. You can.
I see Slido, polling, content. No. Oh my.
Which icon is it?
Yeah, it's on the lower right. You should see like a circle, like a commands icon with a blue dot.
There. All right. I found it.
Okay.
Okay. Where should I go? Go back up to the top and come down, or?
No, I think mostly at the bottom. Mostly at the bottom. Earlier, just people saying hello.
Oh, the reference chart is not online because the fonts are proprietary to JPL. Don't ask me. And you have my address. Write me, and I'll send me a letter and with your address and everything, and I'll mail it back to you. The Whipple shield, yeah. All right, what else? I don't see.
If no question online, no, I actually have a question here. So, how do you think? There's a space tourism balloon. It's called a space perspective. According to the website, it's saying they are going to fly the altitude about 30 kilometers. Do you think that's kind of thing? Probably not long duration. Do you think those kind of space tourism balloon, high altitude balloon, need to have this kind of shield?
Of course, it turns out the balloons can go to about 100,000 feet, and I think that's what 30 kilometers.
Yes.
And that's as high as they can go. I've flown 10 balloons at that height and altitude to study the aurora. And it's perfectly feasible. You just have to make sure the balloon doesn't get a hole in it, which ours did. I dropped one over Russia at 100,000 feet. They didn't like it.
So do you think they should apply the Whipple shield, or is not necessary?
No, you're not, for a balloon, you wouldn't do that.
Okay.
That you're not going to be up long enough. And you have to remember it's a size versus time. And you just take your chances. There's not much that you can, if you were to be hit by something at that altitude, you're going to be in trouble anyway, though. The balloons, fortunately, balloons leak slowly, so you'd probably be all right to come down. And I think they have escape mechanisms for them anyway, parachutes and stuff. At least that's what we did. We had parachutes.
I see. And you when you're modeling your meteoroids, but how do you differentiate? You also mentioned satellite, it kind of broke up, become debris. So I understand doing the model, but in reality, how do you differentiate micrometeoroids?
Mass spectrometer. They use mass spectrometers.
Oh.
That's how they were able to detect the urine in the pit. They actually did trace it back to urine. And so what I'm trying to say is that what they do is when something smashes into you, it leaves the traces of itself. And that's why they cut all the little pieces out of the wide field planetary camera outer surface there. And like I said, they took about 600 core samples. And then they go back and they analyze them to figure out how much is micrometeoroids, how much is contamination, and how much is debris.
I see. So probably mass spectrometry, probably also the way, because you talk about the species material for micrometeoroids, like you mentioned iron meteoroids.
Yeah.
So that's how they detect. I understand for model is a story, but in real life, how do they detect which kind of species is this micrometeorite? How do they know it is iron?
Well, there are two ways. One is when they come in and burn up in the atmosphere, you can make a spectrum of them.
Ah, I see.
And then the other thing is, like I said, they actually they measure them, of course, on the ground when they come down, and then they also, like I said, from the pitting on the surfaces of the spacecraft, they can section those and do a mass spectrometer analysis. That's exactly what they do.
I see. And about the software, you show the software, the JPL software, the window interface. Is that something that is like on some of the software on JPL website, or is more like an internal?
Yes, there's the JPL website that you can go to. Try to remember. Robin, do you have it in front of you? No, I guess you didn't hear me. I don't have. I have to look it up, but I can send that to you later.
Okay, because that sounds very interesting.
Yeah, I can send you the website. We just, in fact, I just gave a talk on Uranus radiation belts, and my colleague Insu Jun controls that website, and he gave all the information how to use it.
I see.
So yes, if you just, I'm not going to remember much of anything from today. So if you send me emails asking for what you want, I'll be glad to respond. That goes for the mailing out the chart. If somebody will send me an email, Robin Evans and I produced that chart.
Yeah, I want one too. I want one too.
Well, you got to email me. I'm not going to remember anything. This is hard on an old man.
No, don't worry, I'm your secretary. I'm your secretary. I remember for you. Oh, by the way, I see Jason. Jason online. You turn on your microphone. Do you want to say something, Jason? Jason, his microphone is on. So, any question online? Um, if not, I do have a question because this is very interesting. Dr. Gary, you show a picture with the shock wave, and you talk about the paint, the effect of the paint. And it seems that from your session one talk about charging, the paint also have some issues. So why do they still need a paint? The paint seems to be falling off. You have issues there. So why? Oh, why do they still need a paint on the spacecraft?
No, they put paint like that on the spacecraft for thermal control reasons.
I see.
And they use a lot of paint on spacecraft for thermal control. White, of course, reflects, is good sort of like insulator, and black absorbs heat. And so they mix black and white on the spacecraft to control the temperature. Almost all JPL satellites are passive in their thermal protection system. They're not like manned missions where they have air conditioners and junk like that. And so most interplanetary probes are not actively controlled. And so by putting thermal blankets and paint, you control the temperature of the satellite. It's a whole field in and of itself.
I see. But it tends to be this is cracking, or kind of issues there. Okay. Oh, by the way, I think you show the press. Maybe I missed something. You mentioned about the photon pressure when you talk about the meteoroids and debris environment. Could you elaborate a little bit about it? Why this photon pressure is an issue there? Could you?
Well, if you remember the reason solar sails work.
Oh, okay.
Sunlight shines onto a surface and then it's reflected. And even though it doesn't have mass, it has momentum. And h nu, what is it? Rho equals h nu over c, I think. And there's a bunch. You can get a bunch of books on solar sailing, and they go into great detail on the acceleration properties of the sunlight and how it works.
I see. Sorry, I missed that part. Very interesting. Almost, Gary, go ahead.
One curiosity I've had through my life is the accumulation of planets and masses in the solar system and the universe. Do your calculations allow for back calculations towards the accumulation, towards the aggregation of planetary bodies and so forth?
Oh, you mean, can I calculate how bodies form in space? I've done a little bit of that. Like I said, I've done some of the commentary. I worked on comets and how they give off particles and how those can accumulate on the surface. But as far as the actual creation of planets and stuff, I haven't done those calculations.
Yeah.
Sorry. But I know people do that all the time. There's an entire field of astronomy in which they do they generate solar systems or suns and stuff like that. I took a course in making a sun in college. And so how it coalesces and then goes through the different stages of burning fuel. But as far as planet aggregation, I haven't done that, except for, like I said, put a surface near a comet and I can tell you how many particles get on it.
It was very much of a straight question, but everybody always says the core of the sun is hydrogen, but
helium.
it would seem to have the same mass distribution as the rest of the solar system, including all the other all the other elements. But yeah.
Okay. By the way, Dr. Garrett, sorry, this is kind of interesting. So, the Whipple shield, have anybody tried to kind of do a simulation or or actual were to put fluid, in between the layers.
You're talking about putting something in between?
That's right, maybe
Yeah,
more.
they have. In
that.
fact, we ran into some problems with that. If I remember, we had honeycomb. It was used to stand off the shield, and we tried to figure out what it would do. And I think we came to the conclusion that honeycomb just focuses the meteorite beam down down the hole.
Yeah, and actually, one other sidelight comment. At the beginning of my career, I worked on the Apollo Command Module, and the adjacent group worked on the. I worked on the pressure shell, well, on the contents, basically. But the adjacent group did the heat shield, and Al Richardson was one of the members of our crew that worked and talked about the Whipple shield as being an effective technique. I'm not sure if that was a result of his work or if he found other people's work at that time. That was about 1967.
Anyway, it works effectively on tanks. In fact,
Yes.
one of the things they do on tanks is they actually put explosive material on the surface of the tank. And so
Yes.
when the projectile hits it, blows it up.
Right. Yeah. Of course, the Apollo and I think the SpaceX Dragon and all similar spacecraft for reentry have the heavy heat shield, which is also another form of meteoroid protection. But at hypervelocity, it actually is easily penetrated. And then there was the honeycomb shell that had thin sheets and focusing hexagonal honeycomb inside to the inner shell. So
That's what I was thinking of. Yeah,
yeah.
that's what we were looking at too. But no, you can put stuff in between. It's just you have to do the math. You have to see what it works like, and you have to test it. And the problem with all these techniques is you can't get the test velocities up to the realm where you need to worry about them. I mean, it's very expensive to do testing, and there are not very many facilities for doing testing, and it's a mess.
Yeah.
And NASA cut back on all its testing facilities back around 15 years ago. They just fired everybody. No, they did.
Wow.
Closed down the stuff at Johnson.
Yeah, University of Washington had a hypervelocity gun.
Yeah, I've been it. I've seen it. I've been there.
I'm sure you have. but that in order to make that work, they essentially have to have virtually a vacuum in the gun itself at the beginning, right? And then they basically explode the gas mixture upstream of the burst disk.
Yeah, if I remember, they use gas and they pump it in there, and then the membrane bursts, and it bursts down to the next one, and so forth.
Right.
And what I thought was interesting is he was showing me how you could almost launch a rocket that way. Well, if you get over 7 kilometers per second, in principle, you can launch it. But those are big guns. I mean, people have developed those. There was a Saddam Hussein gun somebody developed for Saddam. There was like in fact, they had a recent NOVA program on that.
Okay, Elijah, go ahead.
No, nothing else.
Elijah, have any question?
Yeah, I had a question regarding the solar sails you were mentioning earlier.
Yes.
You say that it was what was it? The radiation pressure. It was the thing that was pushing away the meteoroids as well.
Yes,
was that
the
the
same
case?
thing.
Oh, sorry, I apologize. What were you gonna say?
I said same. Yeah, the same thing. Yeah.
So that's the reason why the small meteoroids aren't capable of, or not capable of, they're less likely to hit the solar cell, right?
Right.
Okay, then. I was just trying to understand that more better.
Yeah, the curve turns over. Again, I put my email there. If you email me, I'll send you my calculations. It comes out, I've worked on several solar sail missions and stuff. I've never flown them, but we worked on them.
I-
It's hard to sell solar sails. Say that 3 or 4 times. Hard to sell solar sails.
Yeah.
I have one more question regarding the paints for the spacecraft. I
Yeah,
remember earlier that you said for the what was it? The electrical arcing. You said it was better to not have the white paint, but better for the black paint. But also,
that's the conductive surface. White
Yeah.
paint, most white paints are non-conductive for some, and whereas black paints have carbon in them and are reasonably conductive.
oh, okay, that makes sense because I was curious why that was the case, as well as its relation to thermal properties and having like the black paint be like a proper black body and stuff like that.
Yeah, well, for passive systems, they can do fancy patterns. If you remember, Explorer 1 had black, white, and that was because they wanted to even out the temperatures, if I remember. But on our satellites, we use thermal blankets. We use little RPSs, I think they're called, or HUDs. Anyway, they use little buttons of plutonium to warm things up. And in fact, there's a lot more of those on the vehicle than the RTGs. But no, we passive thermal control is a big deal.
Oh, okay, thank you, Elijah. Dr. Gary Dunn, Mr. Shaw here has a question.
Just a quick question. So the Apollo lunar lander had a thin skin, is what they say. Did that take into account any kind of, micrometeoroid kind of protection?
I don't think they were worried because it was too short a mission. Now, if they'd been out there when the meteorite stream was going by, they would have been very worried. But I think they were careful not to worry about that. In fact, I don't know, have you ever read Michener's book, Space?
No.
You should read it. And there he has a I think it was a 1978 storm. They launched one last Apollo mission to the moon, and it's in the middle of I think it's the 78 storm. And the bottom line is he has the astronaut crawl back up to the land, to the limb, as he dies from radiation exposure from the solar proton event. Really grim. But anyway, the bottom line is that the missions were so short they didn't even worry that much about radiation.
Yeah, the session 1 simulation you show with the astronaut in the charging scenario, that was very interesting. Astronaut, that was very interesting. It's not a question; it's a comment. It's important to understand, the charging or micrometeorite situation, around the astronaut too.
Anyway, we worry about long-term missions. These are tens of years out to the outer planets. So you have to do careful calculations of what the long-term fluences are.
Exactly. So any more question here?
I think I'm good.
Okay, is it okay? So any more question online? I don't see anything.
I put my email address in the chat.
Okay, we also posted online with your title chart.
Yeah, well,
Careful.
Oh, okay.
it's in the title chart.
Okay, so then if no more questions, let's thank Dr. Garrett for this fantastic lecture. So we're looking forward to the next one when Dr. Gary is ready. This is very, very exciting and interesting. So let's thank Dr. Garrett again. Thank you.
Okay, so we done?
We stand.
All
Thank you,
right.
Dr. Garrett, very
Thank
much.
you.
It was excellent. Excellent source of news. Thank you.
Okay. I'm gonna go click out now. I'm leaving the meeting.
Okay,
Right.
thank you so much.
Thank you.
Okay.
I see. Very interesting.